This last example we're going to look at, again, is going to ask us to analyze the graph of this rational function right here. So you can see that I have a lot going on in both the numerator and the denominator. I have three terms. The numerator and the denominator are both quadratics, so let's go ahead and factor this particular function. So the numerator is going to factor into an x and an x. We know we have a subtraction sign here. So I'm looking for factors of 10 that subtract to give me a positive 3. That would be a positive 5 minus 2. I'm going to check my outside outer and inner terms just to make sure I get the middle correct. I have a negative 2x when I multiply here, positive 5x here, and if I add those together I get back the middle term, which gives me 3x. So I have that correct. And the denominator is going to factor into an x and an x. Here I have a positive, so I know, and a positive here, so I have to have two of the same signs. So I'm looking for the factors of 15 that add to give me 8. That would be a 5 and a 3. So we're going to, once we have this factored, let's go ahead and figure out what the domain of this function is. The domain, again, is where the denominator is equal to 0. So we're going to come over here and we say, well, when x plus 5 is equal to 0, I get a something happening, and when x plus 3 equals 0, something happens. So when x is a negative 5 solving this first one and a negative 3 solving the second one, these are the two values which, when I plug them in here, cause the denominator to be equal to 0, and therefore the domain of this function would be I cannot have those two values happening. So x such that, we'll put our set symbol around here, x such that x cannot be negative 5 and negative 3. Those are the two values we would throw out. This is the first example that we're looking at where once we have our function factored, we finally get to reduce. Notice that I can reduce this factor of x plus 5 and this factor of x plus 5, and that leaves me with the reduced rational function of x minus 2 divided by x plus 3. Now, what happened though to my x plus 5? That just seems like it would be important in this function, and I don't want to discount that idea. Remember that when we reduce a function and cancel out one of the factors, this part right here becomes a hole in my graph. Okay, so at x, so for x equal to a negative 5, we have a hole in the graph. And we want to be able to plot that hole or show that hole when we graph this function by hand. So if I have a hole occurring in the graph, then I know that this is at a point. All points on a graph have an x and a y coordinate, so we're missing the y coordinate for when x is equal to negative 5. We're going to find y by, so we're going to find y by substituting x into the reduced fraction or the reduced function. Okay, so I want to know what is the ordered pair, where am I going to be able to plot this hole at, in other words. So we're going to come here and we're going to say, okay, well, y is going to be equal to, I'm going to put a negative 5 over here for x, so negative 5 minus 2, negative 5 plus 3, and when we simplify that, we see that we have 7 halves. So I'm going to write this as an ordered pair. I like to see that when I go back and look at my information. I know that at negative 5, and we're going to call this 3.5, I have a hole occurring in the graph. So that's some important information that comes out of the fact that when I reduced it, I had something going on. Now let's move down, talk again about our x-intercepts. So from here on out, we are going to be dealing with this reduced fraction. Okay, so where do I have x-intercepts? and y-intercepts occurring. So when x is equal to 0, we're going to find the y-intercept. And we're going to do that using this reduced fraction right here. So we have y is equal to 0 minus 2 divided by 0 plus 3. So in other words, at 2/3, and that would be a negative 2/3, I have an y-intercept. So let's just jot that ordered pair down over here. So at 0, negative 2/3. The next thing we're going to look at is where is there an x-intercept. So when y is equal to 0, we have an x-intercept. In other words, we're going to take my reduced function, which was x minus 2 divided by x plus 3, set it equal to 0, and solve. I don't know if you've noticed by now, but technically when I cross multiply, if you see the pattern we have forming here, when I am getting rid of this denominator or multiplying to get rid of this denominator in this particular case, every single time it's just ended up being the numerator equal to 0 when we are finding this intercept. So x minus 2 equals 0, and therefore x would be equal to 2. So this ordered pair looks like 2, 0 for the other intercept I'm looking at. So now I have a hole in my graph, I have an x-intercept, and I have over here a y-intercept. And the last thing we want to look at are the asymptotes. So the vertical asymptote, again, is where the denominator of my reduced function is equal to 0. We know that the denominator is equal to 0. The denominator, I mean, is x plus 3, and therefore it is equal to 0 at negative 3. So I have a vertical asymptote occurring at negative 3. And then for my horizontal or oblique asymptote, we want to look at the degree of the function. So since we are dealing only with this reduced function right here, the degree of the numerator is 1, the degree of the denominator is 1. So we learned that when the degree of the numerator was equal to the degree of the denominator, then we take the coefficients of the leading coefficients. It's the ratio basically of my leading coefficients, which is just a 1 over a 1. So y would be equal to 1 over 1, or in other words, 1. So we have now vertical asymptote occurring at x is equal to 3, horizontal asymptote occurring at y is equal to 1. And I'm going to come down here and I'm going to put all of that information on my graph, and then use my calculator to figure out how to shade it in, or how to draw it in, I mean. Okay, so you can see that I've put everything on my graph already. I went ahead and I put the asymptotes on here. The vertical asymptote at x is equal to negative 3. The horizontal asymptote occurring at y is equal to 1. We had a y-intercept here at 0, negative 2/3, and we had an x-intercept over here at 2, 0, which I have my dot in the wrong spot, but we would want it at 2, 0. So I have those on there, and then I had a hole over here. Remember, we discovered we had a hole at negative 5, 3.5. So that's how I would represent it on my graph. Now I want to come in and plot, show this in my graphing calculator. So I went and I put the function in the y equals, and here is a picture of my graph. Now let's see if I can zoom in on this just a little bit, because I want to show you something that's really kind of interesting on this particular picture. That right here, maybe we'll put it over here a little bit. So here is a picture of my graph that I found that I graphed on my calculator, and notice that on this particular version of the calculator, it's actually showing the hole that we are representing at negative 5, 3.5, which I think is kind of interesting. Yours may not show that. I know that my other personal calculator doesn't have that newer technology in it, and so we want to represent that hole though right here. Most of the graphs typically just show the line extending here and don't account for that whenever we use technology. But if we're doing it by hand, we want to make sure that we represent that. We would never see this hole on a graphing calculator or something else typically unless we were tracing along this line, and then as soon as we got to that hole it would just show up as undefined. So I knew to plot this picture up here in this particular section of my graph, and then I also knew to draw my function over here in this section because of what I had looked at on the calculator. So that's how we're going to go ahead and analyze our rational functions, where we're going through, we're determining asymptotes, intercepts, holes on the graph, and then graphing them by hand or identifying them from something that we have chosen on the computer. So here I have two more. Let me make this a little bit smaller so that you can see this. Here in the notes I have two more examples that I encourage you to go through and practice on, and then check the notes, the completed notes, to see if you're able to get the same answers that I have.